So this is Life of a Pixel. This is a talk that was given by Steve Kobes in 2017 and has been updated since. It is an end-to-end overview about how we render stuff on the web. These slides are pretty dense, and the purpose here is to serve as a resource so that you can come back to this talk in the future. So my name is Philip, and I'm the TL of the Paint team within the rendering team. And I've been at Chrome for about 8 years. And as I hope this talk shows, there are a lot of interesting computer science and software engineering problems in rendering. So we have about 45 minutes to cover 45 milliseconds. So let's get started. All right, so this talk, one of the challenges in a talk like this is that the architecture is constantly changing. This talk is going to be focused on the code as it exists today, and we're only briefly going to talk about the past as well as the future. All right, so what is rendering? So rendering takes content. This is what the web developer has specified, and turns it into pixels. This is like colors on the screen. So we're going to talk about this huge block in the middle called rendering. From a browser architecture perspective, content is the stuff below the URL bar. It's everything in this red box. Within the browser, web contents create renderer processes. These are sandbox, and this is important for the security of Chrome, because an exploit in one web page can't affect another web page. And within the renderer processes is something called Blink. This is what implements the web APIs and does the majority of the rendering. There's also something here called the compositor, which we'll talk about later. So that was content from a browser architecture perspective. But content from a rendering perspective is the stuff that the web developer writes, things like HTML, CSS, JavaScript, as well as resources like images. So HTML, this is a plain text markup language, sort of like XML, or it's based on it. CSS, this is for styling that HTML, for adding color and fonts and things like that. JavaScript is the programming language of the web, and it allows you to dynamically change HTML and CSS. And finally, we have the resources. So just to give a better example of this, a website is just a collection of thousands of lines of HTML, CSS, and JavaScript. This is different from other platforms where you might compile your binary before giving it to the user. On the web, the input to the rendering is the source code that the web developer has written. So this property made the early web very easy to write for. Like you could just type something out and immediately see it in the browser. All right, so that's what content is. That's one end of rendering. On the other end of rendering is pixels. So we're actually not going to talk about how LEDs work and things like that. Instead, we're going to go to the lowest level primitives on an operating system. This is typically OpenGL, but it's also things like DirectX on Windows, Vulkan on later Android, as well as Metal. These low-level APIs give you things like, they allow you to do things like draw a triangle with a specific color. All right, so the goal here is we're going to talk about how to render content into pixels. And we're going to talk about the stages that let you do that. But something to keep in mind is that we don't want to just show the web page one time. We need it to be interactive. And so the second half of this talk is going to be talking about how to design the pipeline such that it can be updated efficiently. So the steps of rendering are what we call a lifecycle. And you have different stages of this lifecycle. And each stage has, in the ideal case, clear inputs and clear outputs, as well as maybe a cache of the intermediate data structures. The first step in rendering is parsing. This is basically straight out of like an intro CSS class. We will do things like we have a byte stream, and we read the bytes, we tokenize those bytes. From that, we create a C++ representation of the tree that they specified in HTML. This is, so here's a simple example. We're showing a div with 2 p tags. P stands for paragraph. And so on the left, you see the div and 2 p tags. On the right, you see the C++ objects that we would build from this. Listed here is the document, HTML, and body element. These are automatically generated. But I think it's, look at the div, the p, and the text below that. So the DOM is what we call this C++ representation. It stands for Document Object Model. Like all trees in computer science, is upside down. And I think it's useful here to talk about the actual C++ object. If you look in the codebase, you'll see something called node.h. It has the parent pointers, the left, right sibling pointers, things like that. So it's very much like a classic tree. So the DOM serves double duty. It is both the representation of the HTML that the web author specified, but it's also the API that is exposed to JavaScript. So JavaScript by itself, it has no rendering ability. There's no graphics APIs in JavaScript. So the only way JavaScript can change things on the page is through the DOM. And we have what's called bindings. This is the link from the JavaScript programming language to the C++ objects we have in memory. Okay, so now we've built this DOM tree. We now need to give it some style. So CSS or styles, these are ways to style each node in this DOM tree. And it's done using selectors. So here's a simple example with a P and color red. This color red is going to apply to all of the P tags in this DOM tree. So in this simple example, we have 2 P tags, and they're both going to be red. So there are tons of styles. I think there's probably thousands. These are things like fonts, colors, backgrounds, as well as transforms. These are the knobs that web authors can use to style their document. Styles can be pretty complicated. Here's a really complicated looking one, but this is pretty typical of what you'd see on a real web page. All this is doing an effect of even odd coloring that you might see, for example, on a table. This complicated looking selector is styling every other P in any div without class foo, and it's going to make it the color red. Notice here that there's a color red for the P tag, and then below it there's another P tag, another selector for P. So these are conflicting. The way this is resolved is using some predefined rules, and this is the cascade in CSS. So how does this really work? Just like the HTML parsing, the CSS parser basically takes this input that the web developer specified and creates a C++ representation of that. So we create style sheet contents, CSS selector lists, etc., until at the end of this pile of turtles, we have at the end a property, for example, border left color, and then a value, for example, blue. So style recalc, what we do is for every node in the DOM tree, we compute the style that will apply to that node. And this is basically just a giant map of properties to values. All right, so styles, these can be seen in DevTools. We can actually see in the highlighted in red here, this is a color blue, and that's the text on the left, and this is the computed style on the right. You can also read this in JavaScript using get computed style. And there's some note that there are sometimes layout properties in here. So there's a few details, but in the simplest case, the styles you see in the computed style list in DevTools are the computed style. All right, so now we've built a DOM, we've computed all the styles. Now we need to determine the visual geometry of the web page, or each node, basically. So here's a simple example highlighted in red with dash red. This text, it says W3C Advisory Committee, something. What is the X, Y, and the width and height of this? For example, the web developer may have said that the width is 100%. But what does that really mean in pixels? And where would that thing go on the web page? Layout is going to figure that out. So for example, if they said this is width 100 pixels and the parent has width of 400 pixels, then layout would say, okay, this is going to be 400 pixels. There are in broad strokes, there are two kinds of layout. There's block flow, which is where blocks flow from top to bottom. If we take a block, the Y position will be equal to the previous block's Y position plus the previous block's height. Another example of layout is inline flow. This is for things like text. So you lay things out kind of left to right, depending on your language. Now, this is more complicated than it may seem because you can even have mixed left to right and right to left text in one line. And we're going to be determining where to break the lines and things like that. This is called inline flow. Okay, so to do layout, you need to measure text. And to do that, there's this interesting kind of subdiscipline of computer science called text shaping. What this is doing is it's determining, you have a font, you have some text, but what actual glyphs are used to show that? In this example of fire has 4 characters, but this is actually rendered using 3 glyphs because we combine the F and the I using a single ligature, it's called. So there's a lot of of interesting computer science stuff going on in the measurements and shaping of text. We use a library called HarfBuzz to do this. And a lot of the engineering in layout is around using this HarfBuzz library in the most optimal way. One thing I need to note here is that layout does more than just compute the X, Y, and width and height. It's also computing some additional blocks. It's also computing things like whether you have scroll bars and what location those scroll bars are at. There are more complicated kinds of layout. The previous inline flow and block flow are pretty simple because they're kind of top-down in a way. Other kinds of layout use more global state. For example, in the table layout, you might need to balance the width of two different cells in the table. Okay, so layout actually computes the visual geometry, and it stores it in an object called the layout object tree. This is roughly a one-to-one mapping between the nodes in the DOM tree that we talked about before. This is not quite true. Here are some examples of why layout objects and nodes are not one-to-one. But unless you're in the layout system, I think it's best to just think of them as being one-to-one. And that simplification works, will go a long way. Okay, so the layout lifecycle stage walks the layout tree, computing the visual geometry and storing it in the layout object. So I need to note one thing. There is currently a rewrite of the layout system called layout ng. Where we are in that rewrite, about 75% of layouts are using the layout ng system, but we still have the legacy system around. Layout ng is a re-architecture that more clearly defines the inputs and outputs of layout. You can think of it as the pipeline. This has a lot of advantages. One advantage is that is performance, because you can more clearly see whether one change affects another part of the tree. But both of these things live together and are both running, and sometimes we'll switch between them. In the future, all layout will be layout ng. Okay, now that we have the visual geometry of our layout objects, we need to paint them. And paint is the step where we're basically going to create a linear list of drawing instructions from this layout object tree. A drawing instruction, or paint op, is a really simple thing. It says something like draw a rectangle, or draw a line, or draw some text at this location. These are very low-level primitives. Now, it's not so simple to go from a layout tree to this linear list. One example is something called stacking layer. Now, when the web developer put their HTML in the page, that goes from top to bottom, but we don't necessarily paint in the same way, because a style can say something should paint on top of everything else, for example. And so when we do this linearization of the layout object tree, we need to make sure to get things in the right stacking order. Another example here is layout objects actually paint in multiple phases. So for example, a div may paint its background, then the foreground text, and then maybe the selection the user has on top of that. So we need to actually process each layout object several times in each of these phases. So the paint lifecycle stage makes several iterations over the layout tree in order to produce this linear list of paint operations. From these paint operations, we then raster them. Raster is the process of turning paint operations into a bitmap of pixels. Now these pixels are still in memory. They're not actually physically on the screen yet. We're going to get there really soon. So a bitmap of pixels is like a matrix where each value in the matrix is an actual color. For example, red or green or blue or something like that. One note that you can actually use the GPU to accelerate this process, and we'll talk about that a little bit more later. Okay, so raster, this is also an interesting subdiscipline of computer science. This involves things like, if you want to draw a line, you don't want that line to be jagged, and so you need to apply something called AntiAliasing, so it's very smooth. It also involves things like, when you're drawing text, you want to use the LCD panels properties in order to make the text look very nice. This is called LCD anti-aliasing. Rasterization is also concerned with things like, how do you blend, if you want to do a blur of something, how do you actually blend each pixel? What does that look like? So the rasterization library we use is called Skia. And Skia is a project that's also maintained by Google, but it's external to Chrome. Skia is actually used by other projects like Android, as well as competing browsers like Firefox. And what Skia does is it takes this input of paint operations and it outputs OpenGL calls as well as Vulkan calls. So we talked before about how the render process is sandboxed for security. These low-level calls into OpenGL are not safe. And so we need to separate the render process from the GPU process. This has some other advantages. For example, these low-level graphics APIs are also kind of crashy. So if this GPU process crashes, we can actually bring it back up without the user ever noticing anything happened. In the past, this would mean your whole browser fell down and you lost like state. So we take these paint operations and we pass them to the GPU process. Then Skia does its calls to OpenGL there. There's something interesting on Windows. Windows, the low-level API is called Directx, but we actually tell Skia to OpenGL, and then behind the scenes, we connect the OpenGL calls to a sub-project called Angle, and this does a conversion between OpenGL and Directx. Okay, we have a full pipeline, at least 2 pixels in memory. Just to go over it, we took the HTML, we created a DOM tree, we styled that DOM tree, we computed the visual geometry of that DOM tree and stored it in a layout tree. We painted that layout tree, which made a list of paint operations. We rastered that using the GPU, and we got this bitmap in pixels. So this is just one shot of a page. It'll splat it onto the screen. But what happens when things change? It's useful to think about change as animation frames. For example, the operating system may say that you need to draw once every 60 frames per second. And if you take too long to do that drawing, the result is going to be kind of jerky. We call it janky. And that's not great. So one like easy solution to this kind of problem is just to make the pipeline faster by using caching. So we definitely do this. To give a concrete example of what this looks like, every layout object has a bit on it for whether it needs layout. And then when you do the layout lifecycle step, we only lay out nodes that needed layout. But this approach only gets you so far. One example of this is scrolling. So if you needed to run the paint and raster steps on every scroll offset change, the scrolling would not look good. In particular, one of the main issues here is that the main thread, the thing that layouts, paints, styles, DOMs, that DOM runs on, is also the thread that JavaScript runs. So if the web developer has some long task where JavaScript is taking a long time, we can't change anything on the screen. So a solution to this problem is called threaded compositing. I think it's useful to think about this as the early animators did, like early cartoon animators. In the very first cartoon animations, every single frame was drawn by hand. You basically had a piece of paper, you drew it, you got another piece of paper to draw the next frame, etc. Disney, I think, popularized this approach of using celluloid film, which is just a transparent piece of paper. So you'll draw the background once, and then you draw your character onto a piece of transparent paper. You hold them both up to take a picture of that. So this idea of using layers is similar to what we do in the renderer. So we actually break up the page into different layers. And then the second part of this is that we combine these layers on a separate thread. On the right here, you see this is my inbox, and it's shown using the Layers tab in Developer Tools. You can see how some layers on top of other layers. So the main thread builds these layers and then passes it on to a different thread called the Impul thread, or the compositor thread. Impul is a poor name. Has no relevance anymore, but it's used throughout the code, and so I think I have to mention it. The Impul thread is the same as the compositor thread. So we have these layers, we pass them on to the Impul thread, which then combines the layers and passes it onto the screen. So I want to talk a little bit more about these layers. Here's an example where this BBB text has been drawn into a single bitmap. And then we don't need to re-rasterize it as we move it around. We just take that transparency sheet and just move it around instead. And this applies to subtrees. Here's an example showing a subtree that's moving around. Again, we've only rasterized this one time, and then we simply move it on the GPU. So there are many examples of fluid animation that can be expressed using this threaded compositing approach. One example is animations, another is scrolling, and another is pinch zoom. So the way this all works is the input comes from the browser process, like the user wants to scroll. The Impul or compositor thread gets a chance to do that scroll. If it can handle it, it'll just do the scroll all by itself without ever talking to the main thread. If it can't handle it, it'll forward the event on to the main thread. So how is this actually implemented? Well, from the layout tree, we actually create layers. This is a new step. It actually uses a similar concept to the stacking thing we mentioned before. There's no hierarchy to layers, they're just back to front. And this layer creation is done in a new step between layout and paint called the compositing update. Now, if all we have is a collection of layers, you can't do anything with that. You need to know like which layers are scrollable or how they transform with respect to each other. So this additional information is called property trees. And we build these property trees in another step between layout and paint called Prepaint. So we just talked about 2 new steps in order to implement this threaded compositing idea. A quick side note that there's an ongoing project to move the composite step after paint. The whole goal here is to move things off of the main thread in the future, because that main thread where the user's JavaScript runs is a precious resource, and we need to avoid using as much of it as possible. Okay, so we have the main and the Impul threads. There's some interesting things here in how CrossThread communication works. So once paint has completed on the main thread, we actually block the main thread. We block the main and Impul threads, and we pass the information from the main to the Impul. Once that's done, we then unlock the threads and they continue on. Now, in the early design where we basically painted what we saw on the screen, we didn't have this concept of overdraw, but now we do. Imagine you have a really long web page. The user's never going to look at that copyright thing at the very bottom, where it's going to be a long time until they do. And so you don't want to have to rasterize this very tall layer. So what we do is we split up the layer into tiles. These are just little chunks of the layer, and we then rasterize them independently. This is done asynchronously. So we take each tile and we send it off to the GPU for skia to raster, and it gives us back a handle to the rastered output. And actually, we can avoid rasterizing ones that are really far away. Okay, so once we've drawn all of our tiles, we rasterize them all. We then package everything up into something called a composite frame. And this is the output of the renderer. And it gets sent to the GPU process. We're really close to pixels now. Something to note here is that we actually double buffer this whole process. The reason is that as we're working on the next frame, we're like sending off these raster tasks, a scroll can come in, and we want to be able to respond to that quickly. And so what we do is we have the tree that we're working on, we're like our scratch space basically, and we have the tree that the user sees. And if they want to scroll, they can continue to scroll while we're still working on this other tree. Once we're done, we swap these. All right, now, so each render process outputs a compositor frame. And these compositor frames are all combined in the Viz compositor thread on the GPU process. Now, also what comes in here is the UI for the browser, things like the tab strip and the back button and things like that. And notice here that there are multiple render processes. They're all talking to this GPU process, the Viz compositor thread within it. And that's because a single web page can be broken up into multiple renderers. So you might have the renderer for the main page, as well as the renderer for an iframe. Viz, which stands for visuals, just combines all of these outputs, then uses skia to draw it on the screen. Now, skia isn't being used here to draw these nice smooth curves. It's just being used in order to draw textures, existing textures, onto the page, because skia is our only interface with those low-level platform APIs. And with that, we're done. We actually have pixels on the screen. Let me kind of walk through this just one more time. We took the HTML content, we built the DOM tree, we styled that DOM tree, we computed the visual geometry of the DOM tree, we stored it in a layout tree. We then made layers from this, as well as property trees, and we painted this all, which is just making a linear list out of the tree. We then passed these painted results along with property trees to the Impul thread, which broke up the layers into tiles, which rastered each tile independently. Once it was done rasterizing each tile, it swapped its buffer. It then passed the final results back to the GPU process, which combined multiple renderers and finally put the result on the screen. And that's it. So this is a living document. I went really fast because this is pretty complicated. But these slides are going to be available for here, and hopefully they'll be updated as we go in the future.